Mastery in teenage emotions. Uh, let's talk about that. With a quote from Nodding's 2003, happiness should be an aim for education, and a good education should contribute significantly to personal and collective happiness. The OECD, Program for International Student Assessment, or PISA, examines what students know in reading, math, and science, and what they can do with what they know. It provides a comprehensive international assessment for students' learning outcomes. Results from PISA indicate the quality and equity of learning outcomes attained around the world and allow educators and policymakers to learn from the policies and practices applied in other countries. In the recent PISA 2018, on average, Canada ranked well. Canada ranked 6th in reading, ninth in science, and 12th in math. This achievement is multifaceted, with intersections coming from health, economic, and psychological domains, and a myriad of others. In this study, I'll be looking into mastery, subjective well being, and how these two are related to math ability. Looking at mastery versus performance goals in students, simplified, performance is grade oriented drive, and mastery is learning oriented. First, performance goals focus on achievement based on normative or comparative standards of performing. Performance goals then lead to focus on the outcomes rather than the process of learning, such as achieving success by any means, avoiding the appearance of being incompetent, and being more susceptible to extrinsic sources of motivation. Mastery goals, on the other, focus students' attention on achievement based on intrapersonal standards of learning. When students adopt mastery oriented goals, they engage in more effective learning strategies, such as learning from their mistakes, changing strategies that don't work, and seeking out help when necessary. Mastery oriented students are also more intrinsically motivated, arguably the best fuel for motivation. Closely at mastery, we can look at mastery motives and goals. Throughout this presentation, I'll call mastery motives interchangeably with work mastery. The key distinction here is between motive and goal. Work motives are implicit reasons for doing something, whereas mastery goals are explicit. For example, agreeing to the statement, I find satisfaction in working as hard as I can, is related to the practice of mastery but is not as direct compared to the statement, my goal is to understand the course content thoroughly. In the second statement, one is explicit about the reason they're striving mastery. Motivational research has proposed that these constructs are predictors of subjective well being. As an introduction to subjective well being can be viewed as both as cognitive appraisals of the quality of one's life as a whole and as experiences of positive and negative affect. As it applies to school, subjective well being pertains to how students subjectively evaluate and perceive their school lives and experiences. Affect then refers to the student's frequencies of experiencing positive and negative emotions. As a gold standard of achievement motivation, mastery is associated with positive school outcomes and subjective well beings. In this study, I'll be looking into how our emotions as positive and negative affect related to mastery motives and goals, as they are then related to math achievement using PISA 2018 dataset. To answer this question, first I'll be selecting items from the PISA data relating to subjective well being, mastery, and math achievement. Then, using the shortlist items, I will conduct a factor analysis to identify the factor structure, and then use structural equation modeling, or SEM, to fit the data into latent factors. Lastly, I will test the SEM model in part using moderation analysis on a random subsample. Let's get started. First, defining the subscales. Inspecting the PISA data, there is an overview of the teenage Canadian participants grouped by female and male gender and age 15 and 16-year-olds. On average, reported math scores suggest a small gender difference. We can also infer here that for the Canadian sample, this small difference may also be in effect. Also, there seems to be a small gender difference in subjective well-being. And in terms of mastery, I'm inferring work mastery as mastery motives here. So work mastery and mastery goal perspectives seem to be higher in females versus male teens. With this, I recognize that gender and age could be possible covariates that may influence the main study variables. In operationalizing our conceptual variables to fit the PISA data, I will discuss the main subscales for this study. Here are the subscales used for work mastery and mastery goals. Both are 4-point Likert scales. Work mastery asks the students how much they agree on the following statements relating to mastery, whereas the mastery goal condition, they're asking how much of the following statements are true to them. Work mastery statements are more implicit and subtle reasons for mastery achievement, recalling mastery motives, whereas mastery goals are more explicit and internally about mastery, asking questions like, my goal is to learn as much as possible, ... Reliability for both subscales are above alpha 0.7, so that's pretty good. To operationalize subjective well-being, I used affect, or the frequency of experiencing positive and negative emotions. PISA recorded these 8 emotions. Both were reliable with at least 0.8 alpha, so also a good set. PISA, as advertised, assessed math literacy. For this study, I used 2 of the predicted math scores as the main outcome variables. A math score represents the student's ability to reason mathematically and use math concepts, procedures, facts, tools to describe, explain, and predict phenomena. I chose a math score pair that has the best reliability coefficient. The 2 I obtained had a reliability of 0.88. With the items chosen, I used them to drive part 2, the factor analysis. To test EFA assumptions, the inter-item correlations vary between small correlations, or the gray ones, and large correlations, the bold numbers. But that's expected. There's no correlations over 0.9, so there's no detrimental collinearity. To test for independence, I used the Bartlett test of sphericity. Here, it's shown it's significant. In other words, all the variables are unrelated enough to each other. Also, the KMO measure verified that the sampling adequacy for the analysis, or KMO equal to 0.81, is good according to the rule of thumb, and all other KMO values for individual questions were equal to or greater than the acceptable 0.5. This means you can proceed with the EFA. From the scree plot, to roughly determine the number of factors, we can see taking 5 factors, which is what we want. Using EFA with principal axis extraction method and with an orthogonal Varimax rotation, the 5-factor structure is confirmed. With the 5 extracted factors, their combination explained 58% of the variance. Now it's time to build the model. Considering there are over 18,000 samples data, I'm assuming normality of error distribution to satisfy the use of maximum likelihood estimation model method. So, with the 5 factors obtained from earlier, I tried to fit the PISA data accordingly to this 5-factor model. Again, with the very large sample size, chi-squared based indices will probably not be significant. Otherwise, the other model fit indexes turned out well. TLI and RMSEA were reasonable. CFI is almost at 0.95. So inspecting the modification index, the pairs scared and afraid and sad and miserable are very sensible covariates, so I added a path to those lines. With this modified model, the fit is much better for CFI, TLI, and RMSEA. Here's the rest of the Lavard output for the optimized full model. So, are random emotions related to mastery and math achievement? Yes. How are emotions related to mastery and math achievement? Here is a pretty version of the model. Given the sample size, all factor loadings are significant. The dashes are covariate, and the solid lines are connectors between the indicators and latent variables. The shades indicate the strength of the relationship. Lighter ones are small effect, and the darker ones are stronger effect. The red lines are negative associations. You could notice that they're primarily coming from negative affect factor. High negative affect is negatively associated with other factors which are mostly small. Interestingly, except with regards to negative affect and work mastery with minus 0.28. Positive affect is positively associated with work mastery and mastery goal with a moderate effect size of 0.3 and 0.35 respectively. Our emotions, represented by positive and negative affect factors, are both weakly correlated with math ability with 0.04 and minus 0.02 respectively. Work mastery and mastery goal have a strong association with each other with 0.63, and both work mastery and mastery goal are similarly associated with math ability with a small correlation of 0.16. All correlations presented are significant. To get a better look, I ran an SEM with moderation. So with the regression paradigm, I'm asking these 4 questions. Does work mastery predict math scores? Does negative and positive affect predict math scores? And lastly, does positive and negative affect moderate the relationship between work mastery and math achievement? To answer these questions, I'm interested in a portion of this model from earlier. I'll only look at work mastery and math ability and test if positive and negative affects are moderators to that relationship. So it looks like this if negative affect is a moderator, and it looks like this if positive affect is a moderator. To do this, I selected 350 students at random from the original 18,000 Canadian students from the PISA data. Then, using the original model, I predict their latent scores for math ability, work mastery, and positive and negative affect. Lastly, with their predicted scores, I ran a regression with moderation to test for significant interactions. Here's how the data fits the negative affect as a moderator model, the dashed lines are not significant, and the solid lines are significant. Here are the loads and the factors. Here, work mastery predicted math ability with a small effect of 0.18, but not for the main effect of negative affect, which is negative 0.04, and the interaction effect, which is 0. Here's the Lavaan output, and the reduced model fits indexes. Here's the full model from R. So using the resampled 350 teens, I followed up with a regression analysis with simple slopes analysis. Here are the results. Here we can see higher mastery did predict better math scores, controlling for negative affect. The parallel lines show no interaction between negative affect and work mastery. Interestingly, students with higher predicted negative affect scores, or teens who reported being miserable, sad, afraid, or scared, on average had lower math scores, shown in the graph in yellow. Compared to the blue line, students with low negative affect actually had the higher predicted math ability scores on average. Correlations from the moderation model are related back to the optimized model. 0.18 is fairly close to 0.16, and the non-significant negative 0.04 is to negative 0.02. The interaction was not in the original model. Moving on, here's how the resampled data fits the positive affect as a moderator model. The dashed lines are, again, not significant, and the main effect of positive affect with 0.05, and the solid lines are significant. Now, in addition to work mastery predicting math ability with a small effect of 0.17, the interaction of positive affect and work mastery is also a significant predictor, indicating that positive affect is a moderator. Here are the goodness of fit indices. Here's the full output from R. Like before, I followed up with a regression analysis with simple slope analysis using the same 350 resampled teenagers. Here's the regression output and the graph comparing the simple slopes. Here we can see higher work mastery again did predict better math scores, controlling for positive affect. This time, we observe intersecting lines indicating an interaction effect between positive affect and work mastery on math ability. In students with low work mastery, or left in the axis, those with higher positive affect scored better in math than those with low positive affect. Meanwhile, on the other end of the x-axis, or the students with high work mastery, the blue line illustrates that students with low positive affect had much higher math ability score. And represented on the yellow line, students with high positive affect didn't really receive much higher marks. The simple slopes analysis revealed a non-significant slope of 0.05. Correlations from the moderation model can again be related back to the full optimized model, 0.17 as the main effect of work mastery and negative 0.05 as main effect of positive affect. Again, the significant interactions were not represented in the original full model. Comparing the two analyses side by side, we can see no interaction for negative affect as a moderator and an interaction effect or moderating effect of positive affect on the right. So in summary, in the one resample experiment scenario, the moderation analysis finds support for the main effect of work mastery predicting math scores in both moderation models. Both negative and positive affect did not significantly predict math scores directly. Lastly, negative affect was not a significant moderator in the resample experiment in the left, but positive affect on the right was observed as a significant moderator seen through the intersecting lines. In sum, this study describes how emotions, positive and negative affect, were related to mastery through work mastery or mastering motives and mastery goals, and also relating it to an academic outcome, math achievement. Also, through the one resample scenario, this study found support for the main effect of work mastery on math ability, and additionally explored positive and negative affect as possible moderating variables. PISA data and results indicate the quality of learning outcomes attained around the world and allow educators and policymakers to learn from the policies and practices applied in other countries. Shown here are Canada's average PISA scores dating back 2003. At face value, these declining national numbers are worrying. Is grade 10 math becoming more hard, or is it becoming more difficult? Are students not studying enough, or are they not receiving the content that is being tested? There is a lot to unwrap here. There is pressure on students to achieve. Additionally, there's pressure on educators to counter this trend, but at what cost? Higher math achievement seems to be associated with higher negative affect and lower positive affect experiences. Findings from this study only looks at a portion of what may be happening here. More research is needed to further understand the relationship between emotions, motivation, and achievement of Canadians. As a point of departure, there exist theories between congruence of internal motives and external goals. Personal goal orientations are associated with high emotional well-being when they are congruent with motive dispositions. In contrast, personal goal orientations are associated with low emotional well-being when they are incongruent with motive dispositions. With pressures to achieve come additional stressors for teachers and the students involved. In students, these may then impair their emotional well-being, especially when students are not able to cope, because teens are often not aware of their unsatisfying beliefs, motives, and goals. Motives and goals incongruence can be conceived as a hidden stress factor. More research is needed to identify factors to explore how one can reach congruence of explicit personal goals with implicit needs or motives. Additionally, this study only looked at mastery motives. Future studies can look into both mastery motives and mastery goal together, and if positive or negative affect may have an influence in congruence. Here are my references. Thank you to Dr. Johnson Lee and to everyone who watched. Feel free to email, or if you have any feedback, please let me know. Thank you.